Okay, so we are looking at rule based systems, power chaining systems, and now we want to look at the inference engine. Okay. So, the inference engine is basically a program which works in 3 phases. The first phase is called match, and what it takes as input is a set of rules and some data and produces a set of matching rules, which in their terminology is called the conflict set. So, it produces that data. Okay. So, let us first see what this match is doing. So, if we have this rules, then notice that we have written these 2 rules in the last class. This rule has 3 conditions 1, 2, 3. This rule has 4 conditions. This is 1, this is 2 and 3 and 4. One of them is a negative condition. So, essentially a rule is a collection of patterns and actions. As far as matching is concerned, we are only interested in patterns. So, we can think of this as P11, P12, P13. So, that is for the first rule. Then P21, P22, P23, P24. So, for this rule for example, and then so on. So, P, K, R or whatever, depending on how many rules you have and how many patterns each rule has essentially. So, that is a rule memory, and when Simon and Newell were talking about this kind of problems, they would associate this with a long term memory. So, basically rules capture the problem solver's knowledge essentially, which is always there with the problem solver. So, you can think of it as long term memory, whereas the actual problem that you are trying to solve sits in memory which we call as working memory, or WM, which is also ordered. So, you have these data elements which we call working memory 1. So, this is the data item 1, then 2, and so on essentially. Now, remember that the actions on the right hand side of rules are allowed to delete data, which means they might delete some working memory element. So, some things might vanish on the way, but initially let us assume that we have some capital N number of working memory elements. Now, this can be thought of as a timestamp, which says when was this working memory element created, and as far as we are concerned, time is just an ordering. So, this is the first element, second element, third element. We will see that this plays a role in the control of the execution essentially. So, we can also think of these as short term memory. If you want to think of this as how we solve problems essentially. Okay. So, we have these 2 memories. One is the working memory which contains these working memory elements, and we saw examples of that. The other is the set of rules where each rule consists of a set of patterns. So, this rule has 3 patterns, this rule has 4 patterns and so on and so forth, and these are the examples of such rules essentially. Now, for a rule to match, now the first task is to match. which means look at all the rules, look at all the data and compute which rule matches with which data. So, if you look at this first rule for example, it says that to play any card, it does not specify which card to play. Now, if you are just starting the game and let us assume that this rule we are. So, let us say this is one of the working memory elements is this here. So, let us say this one is turn to play S. So, let us say S is the name of a player. So, it is S's turn to play. So, there is a piece of data, here there is a pattern which says turn to some variable name. So, this will match with this with this data essentially, and let us say this element is suit to play, let us say clubs. So, this is a working memory element which will match that pattern, second pattern there, suit in play. In play, this is a constant, the data will only have constants, variables are only in the patterns, and if a pattern has a variable, it means it can match anything essentially, whether this was clubs or diamonds or hearts, that rule would still match essentially. And then look at this third element, that player P, in this case P is S, has some cards of, let us say this player has 6 cards of clubs. So, there would be 6 card this player is S and suit is clubs, let us say name is 3. So, let us say he has a 3 of clubs and he has a 7 of clubs and the 9 of clubs and the 8 of clubs and the jack of clubs and the queen of clubs. So, let us say this player has got 1, 2, 3, 4, 5, 6 cards of clubs essentially, that is reflected in 6 working memory elements in which says, and each memory element is saying that there is this 3 of clubs, it is held by S. So, let us just say S stands for south essentially. Now, you can see that this rule, the first rule will have 6 instances, for each of these 6 cards one instance of that rule will fire, will match rather. So, one instance will say yes, it is South's turn to play, the suit in play is clubs and he has got the 3 of clubs. Another instance of that rule will say yes, it is South's turn to play, the suit in play is clubs and he has got the 7 of clubs. So, like this for each of these cards one instance of the rule will fire, and there may be of course many rules in the system, and each will have some instances which would be ready to fire essentially. So, the task of match, this first part of the inference engine, is to compute this set of instances of rules and the corresponding matching data and put it into this set which they call as a conflict set. So, if this is rule, so let us say I call this rule 1 and this is rule 2, then my conflict set will have something like rule 1 matches with first, second and third working memory element, one first, second, third. So, let us say this is rule 1. Another entry into my working memory element, into my conflict set would be rule 2 matches with 1, 2 and let us say 4. Another one would be rule 1, rule 1 matches with 1, 2 and 5. Let us say where 3, 4 and 5 are these elements. So, this is the third one, the fourth one and the fifth one. This is saying that this is an instance of rule 1 which is, so these are the timestamps we are using from that working memory. It is matching working memory number 1 and 2 and 3. This one is matching, the same rule is matching 1 and 2 and 4. This one is matching 1 and 2 and 5, and likewise for rule 2 and rule 3 and whatever rules we have. This set is called the conflict set, and the objective of the first phase of the algorithm, which is the match phase, is to compute this conflict set. Why do we call it conflict set? It is like each rule is clamoring to say I will execute, and so on. So, there is a conflict between all these rules, but you can execute only one rule at a time, assuming that we are talking of a sequential system here. So, people talk of parallel systems in which parallel rule firings take place, but we will not get into that here. What is the complexity of this task? How difficult is it to compute this conflict set in terms of how many operations, how many comparisons you have to do? So, the brute force algorithm would take the first pattern, which is P11, which means the first pattern of the first rule, and try matching it against all these things. Then it will take the second pattern of the first rule and try matching it with all these things. Then the third pattern of the first rule, try matching it with all of this. Then it will go to the second rule. I mean, here you do not even have to distinguish between rules, we just have a set of patterns. So, each pattern in this, it will try to match with each of this, and at the end of it, it will compute the conflict set. Just keep this in mind. So, this conflict set is the set of rules which is ready to execute. So, we use the term execute or fire. So, rule is ready to fire essentially. We give this conflict set to a step which is called resolve, and what it does is that selects a rule. So, there is another program or another module of the program which looks at this conflict set and picks one of them to fire essentially. Now, obviously, what this resolve needs is strategy. What is your problem solving strategy? Given that many rules are ready to execute, which rule should we select to execute actually essentially? Now, there are different kinds of strategies. So, one strategy which is called LEX in Ops 5 terminology or lexicographic strategy. It says that choose a rule that matches or that makes the maximum number of tests. And what do I mean by test? By test I mean each individual this thing. So, for example, I will match the class name with the working memory element. So, that is one test. Then I will match the value of this attribute to play with the working memory element, that is the second test, third, fourth, fifth, sixth, seventh, eighth test. So, this rule has 8 tests that it is doing. This rule has a little bit more tests than it is doing. So, the LEX strategy says that choose a rule that makes the maximum number of tests essentially. So, what is the strategy essentially is doing? It is saying specificity. In other words, it is saying choose the most specific rule which matches. Now, if you look at these two examples that we have, in these two rules, one rule is saying that if you have to play a card of suit S, and if you have a card of suit S, play that. This rule is saying if you have to play a card of suit S, and if you have many cards of suit S, then pick the one which is the highest or highest rank card and play that card. Now, obviously, given any data that I have, so for example, I said that we have these 6 cards, right. So, this will have rank 3, this will have rank 4 and so on and so forth. Both rules are matching, both rules 6 instances of this rule will match and 1 instance of this rule will match. So, there are 7 rules which are trying to tell me which card to play essentially. So, 6 rules are saying any of these cards, and the 7th rule is specifically saying this card queen, which is of highest rank. Why? Because we have said that if the rank of this card is R, then there is no card held by this player whose rank is higher or higher than R, which means the number is lower than R. So, this rule is more specific than this rule. So, this conflict resolution strategy as it is called, which is specificity, will choose the second rule essentially, or if the second rule matches it will. So, you can see that this strategy allows you to implement what we sometimes call as default reasoning, which says you write many rules essentially. So, it is like saying one rule says if you are hungry, go to the mess and eat essentially. The other rule says if you are hungry and you have lots of money and you do not have an exam tomorrow, then go out to a restaurant and eat essentially. Now, the first rule is less specific than the second rule. The second rule requires many conditions to be true, that you should have money, you should be free and that kind of stuff. If both rule matches, then the second rule would be selected. If only if the second rule does not match, that means you do not have money or you are have an exam tomorrow, then that rule will not match, and then only the first rule will match and that will execute. So, you can see that the more specific the rule, the greater we would like it to be selected, and specificity says exactly that choose a rule which is making more number of tests out of the competing set of rules essentially. Another strategy is looking at the timestamp, which is called recency. It says choose a rule that matches the most recent data. And what do we mean by most recent data? Is basically this timestamp that we had said, which has the highest timestamp. So, if every rule will match certain number of elements, remember, for example, this is matching 1, 2 and 3, this is matching 1, 2 and 4 and so on and so forth. Whichever rule is matching the latest data, choose that rule essentially. What is the intuition behind this strategy? It is to kind of maintain a flow of reasoning essentially. So, just imagine you are doing theorem proving, you are proving something. So, you have proved some lemma 1, then you want to use lemma 1 to prove lemma 2, and this rule will allow you to do that, because lemma 1, which is whatever that lemma is, would be the latest entry into your database, and if a rule is matching that, that will automatically get selected. So, it sort of helps in maintaining a chain of reasoning. There is a third strategy which is called MIA, which stands for, maybe at some point we will discuss this, means, ends, which is due to Simon and Newell, and it essentially combines these two by saying recency of pattern 1, and if there is still a conflict, then specificity. So, I should write else. So, by this I mean that you are only looking at the recency of pattern 1, and pattern 1 is the first pattern in every rule essentially. So, this is the first pattern, this is the first pattern, this is the first pattern and so on. So, the first element which follows after the rule, look at the recency of that, and as you can see all these are same, but some other rule may have a higher recency and use that essentially. If there is still conflict, that there is more than one rule which is in contention, then use specificity to choose between them essentially. So, that is why I written else specificity. So, what is the intuition behind this? Essentially, you can partition your rule sets into groups which will solve particular problems essentially. So, let us say you are making dinner essentially, okay. Then you might have a set of rules, let us say, to how to make sambar, and another set of rules of how to make sabji and so on and so forth. Now, if you in each of those rules, if you have the first element which says something like making sambar or making sabji or making chapati or making rice, then the moment you create a context for saying okay, now I am making rice, then you will add that data element saying making rice, that will become the most recent, and all the rules which are concerned with making rice, they will get priority essentially. And that is done by the fact that recency of the first pattern. The first pattern is setting the context, making rice, making tea or whatever essentially. The moment you say this is my task I am doing, only those rules which have that as the first pattern will be in contention, the rest will not come into play. So, you can see it is a combination of these two things. It helps you keep focus to what you are doing, but it also tries to see which rules are best and so on. Now, one more thing is refractoriness. This simply says that the same rule cannot fire with the same data again essentially. So, this comes from some neurobiological studies which says that when neurons are firing, then once a neuron gets a certain set of inputs, they can only fire once with that input, and then there is a period of refractoriness in which they are not active at all essentially. But from our point of view, we can see that we do not want the same rule to fire again and again and again essentially. So, let us say you are doing a classification task, or let us say the task is to classify students into grades essentially. So, you have said if a student has got more than 95 and he has done all the assignments, then give an A grade, and this let us say this rule gets selected and it fires. So, you are already done with the task of giving the A grade or classifying the student as a A student. You do not want that rule to fire again essentially with the same piece of data, and that is what refractoriness says, that every rule can only fire once with that piece of data, which means of course, with the same timestamps in the working memory. If you were to delete some data and add the same data again with a new timestamp, then it could fire, that is a different story. And then, so it selects a rule and gives it to a module called execute, and what this execute does is to applies the actions. Of selected rule. So, remember that this resolve module resolves the conflict between all these rules and says this is the rule that is going to execute, and this execute module basically takes the rule and takes its right hand side, which is the actions, and sort of executes those actions. So, remember what are the actions, things like make or delete and so on essentially. So, what is this doing? It changes the working memory. The effect of execute is to change the working memory. It may add some new data and it may delete some old data from the working memory. So, now you have a new working memory, and now you have to go back all the way and do the match all over again. So, this is the algorithm which this is in some sense a high level algorithm. Actually, you do not implement it like this, we will see how it is done, but you can think of it as doing like this, that first there is a match phase which looks at all the rules and all the data, and by that mean everything in the working memory, and creates this set or this list of rules and the corresponding timestamps of the data elements they are matching. then resolve looks at this set and picks one element out of that and says this is a rule that we will execute. And then when execution happens, the right hand of the side of the rule may make some changes in the working memory. So, some elements are deleted, some may be added, and then we go back to matching again and selecting a rule and so. So, we keep doing this till some termination criteria, which could be that either the conflict set becomes empty at some point, which means no rules are matching, or we have an explicit halt statement somewhere in the program which says under if you see a certain pattern, then you halt and execute. So, let us now discuss the complexity of this whole process. What can we do to improve this essentially? Now, empirically people have found which is the hardest part of this in terms of complexity. Which one will take the most amount of computing time, match or resolve or execute? Which one will take the most amount of time? Look at the complexity of each of the tasks. Look at this task, execute. What is it doing? So, in this example, the right hand side has only one action, which is to add one working memory element with this particular this thing. So, you can see it is a little bit of work. What does resolve have to do? Resolve has to look at this entire set of matching rules or the conflict set and apply the chosen strategy, whichever the strategy we have chosen, to select one of these from this. And what does match have to do? Match has to look at the entire set of rules or the entire set of patterns we have, compare it with the entire working memory and try to find out what is the conflict set. So, obviously, this is a largest task. The number of comparisons you have to do, if you have k rules and each rule has, let us say, p patterns. So, k into p patterns totally, and each pattern may have a certain number of tests essentially, and then all these working memory elements. So, which each you have to find. Remember that you want to find every rule that can possibly execute or every rule that matches. It is not that you are, if you find one or two rules with match, then you are done. All the rules with match, the complete set must be this conflict set must be exhaustive. It must consist all possible rules which are matching. So, this is really the most time consuming part of the algorithm, and people have observed that match takes up something like 80% of computation time. So, just like they say in an industry that most of the time of computing is spent in sorting, for example, most of the time in forward chaining inference engine is spent in matching essentially. You could have other strategies which I have not mentioned here. If you know how Prolog works, Prolog will take the first rule with matches. So, it sort of goes down the program and the first rule with matches it applies essentially. It does not compute all possible matches and then selects one. So, that is a different strategy, that is the something like order of rules or something like that. Here we are considering rules to be floating in some space and there is no order, and any rule is as good as any other rule. So, okay. So, what Charles Forgy, so you should look up some of these terms, either OPS5 or Charles Forgy, or this algorithm which he developed, which is called the Rete algorithm, which is what we want to study, but I think we do not have enough time today. So, we will do it in the next class. Charles Forgy devised the Rete algorithm in 1979, his PhD thesis at CMU, and subsequently it became a commercial product. It is available in any this business rule management engine you talk about. It uses some variation of Rete for matching rules, because it is really the hardest part of doing that essentially. So, this is of course available to us, that we have a paper written by Charles Fogy, and you can find it on the net, which talks about this Rete algorithm. And then he went on to develop an algorithm called Rete 2, and from then onwards they stopped disclosing their algorithm to the public, because they had commercial interest. They had this company which was selling that algorithm, and they did not want to divulge this trade secrets, as they say. And eventually he wrote an algorithm called Rete NT, for those of you who are familiar with Windows, will see the influence of Windows here. So, just around that time Windows NT came, it was a new thing, and so this Rete NT was a new thing. This Rete NT is supposed to be 500 times faster than this original Rete algorithm, which means it takes 500 times less time to do the same match essentially. And you can see that is a great improvement. Instead of having to wait a few minutes, you might have to just wait a second for your match to be done essentially. Unfortunately, we do not know the algorithm, we will only look at the Rete algorithm. Rete itself, the word Rete is a Latin word which means the net essentially. And what this Rete algorithm does is to it compiles the rules into a network, which we will see in the next class, to improve upon the efficiency of match. So, what we want to do today now is to observe where does the inefficiency come from in matching these things. There are two sources of inefficiency, and can you think about them? See, one is the following, that you have many rules, and each rule has some number of patterns, and those patterns have to be matched with data. Now, if you look at the two rules that I have written, we have this pattern, turn to play P. So, it must match a working memory element whose class name is turn, and whose to play attribute must match something. There must be something in this thing. It could be south, north, east, west, to use the terminology from Bridge. This rule also has the same pattern. So, this one could be here, for example, and this one could be here. Likewise, as you can see, the second pattern is also the same, suit in play S, suit in play S. So, this and this are the same. Why should we spend computational time doing this match separately? Why not once and for all say whether this is matched, then we can tell this rule that it is matching, we can also tell this rule that this pattern is matching. So, if we can reduce that, then we will save some time essentially. Not only that, in this third pattern, certain things are common. So, card, suit, play, this thing. This also has card, player, suit, name. It has an additional thing called rank, but at least for those 3 tests or 4 tests, we can share those 4 tests. So, the first thing that we would like to do is to share the tests that different rules are doing and different patterns are doing. So, that as far as possible each test we make only once, or each pattern we match only once. So, if we match this pattern once and then both the rules come to know about it, then we are saving time essentially. So, that is one. So, this is one source of inefficiency, or one avenue for increasing the efficiency of your match algorithm. But there is another which will occur to you if you look at what this execute is doing. What is this execute doing? It is making some new working memory elements, or it is deleting a few working memory elements. So, in a large working memory of this kind, so let me rub this off. So, what execute might do it might send a signal that this is to be deleted. So, I will use minus sign for deletion here. It might say this is to be deleted and it might say new one to be added. So, typically a rule when it executes, it will delete maybe a couple of elements from the working memory, it may add a couple of elements to the working memory. Now, what is it doing? After it executes, it goes back to the match, and at least if you look at it from a brute force point of view, it is going to match all the rules with all the data all over again. Does it need to do that? Now, if you look at this first rule here, which says play any card, it is adding one working memory element essentially. And let us say I had 100 rules for playing cards, and all of them I had done the match in the previous cycle, and all of them are matching, let us say 2-3 instances. So, I have 300 or 400 instances of rules which I matched in the last cycle. What I have done when I executed this rule, let us say this was executed for some reason, or this one is executed for some reason. I have added one working element to my this thing. So, why should I match those other 99 rules again? In this particular example, I am only adding one working memory element and assuming that those 99 rules do not have negative clauses. Even if they have, why should I do that match all over again essentially? Rule number 2, rule number 3, rule number 7, they were matching with some data which is nothing to do with these 4 data elements that we are talking about. Maybe some rule was matching a data here and a data here and a data here. If it was matching in the last cycle, it will match in this cycle as well. So, essentially what the Rete does, so what is the match doing? Match is taking rules and data which is working memory and producing the conflict set. The Rete is an algorithm, or the Rete algorithm is an algorithm which uses a structure called the Rete, or let me just use algorithm here. Takes as input changes in working memory, which is what this execute action is doing. This changes in working memory, it is changing, it is deleting a few elements and adding a few elements. This algorithm, Rete algorithm, takes changes in working memory and gives you changes in the conflict set. So, compare this with this thing, this match here. What match is doing is taking the full working memory, taking all the rules and producing the conflict set, and it is doing this every time we are going through this cycle. Every time a rule fires, it goes and does match all over again. What the Rete algorithm does is says, tell me what are the changes in the working memory element, and it computes that as a result what are the changes in the conflict set. Okay, so, obviously, as you can imagine, this is much less work as compared to doing the full match all over again essentially. We only have to see the effect of these changes into the conflict set. Maybe if I, because of adding this, maybe because of deleting this, some rule which was firing matching earlier will not match now. So, I should be able to know that essentially. Likewise, if I add this, some new rules may come into the conflict set, and maybe some rules might even go out of the conflict set if there was a negative clause here. I should be able to capture that essentially. Okay, so, in the next class we will look at this Rete, which is basically a sort of a discrimination net, or you can, some people use other terms like many sorted network, or it is a generalization of a tri structure, but basically it is a network which discriminates between different kinds of data essentially. You might even think of it as the extension of a binary search tree, which discriminates between only one kind of data, which is numbers. So, it sends you down one branch or the other. The same principle holds, except that this is a multifaceted data, and we have different kinds of tests which are being. So, we even have a test which says that the rank is less than R or rank not equal to R or something like things like that. So, all those tests should be able to be done. So, we will take this up in the next class, which is on Friday, and complete this part of the this thing. Okay.